Hello everyone, my name is Subham and welcome back to my YouTube channel. So in this video we will discuss the properties of congruence modulo M and we will discuss the proof of that properties also, right? So let's start with the first property, that is if A is congruent to B in modulo M, then A plus C is congruent to B plus C in modulo M. Right? What we did? We added a natural number. So what we did? We added a C constant to both sides, right? In A also and in B also. Then what will happen? The new numbers will be in congruent modulo M, right? Now instead of that, if I multiply also by C, then also this congruency will not change. Then also they will be congruent in modulo M. This is fine or not? Now see here, this A, B, C and D are integers and this M and are greater than equal to 2, right? So this is my property. Let's see with one example, right? That will help you to understand. So if I take my A value as 3 and B value as 5, then 3 and 5 are congruent to modulo 2, right? Now if I add 1 on both sides, then 3 plus 1 will be congruent to 5 plus 1 in modulo 2. Why? Because 3 plus 1 is 4, right? And 4 divided by 2 remainder 0. And 5 plus 1 is 6 divided by 2 remainder 0. So 4 is congruent to 6 in modulo 2. Similarly, if I multiplied this number 3 with 2, then that will be congruent to 5 into 2. See, why? Because this is 6. 6 divided by 2 is remainder 0. 5 into 2 is 10. 10 divided by 2 is remainder 0. Right? Or if I multiply with one constant or I will add, then the congruence will not change. Right? Then the new number will also be congruent. Now let's move for the proof. See, 3 is dividing 9. So I will write 3 divide 9. 4 is dividing 8, so I will write 4 dividing 8, right? So this is a symbol for using that this number 3 is dividing 9 and 4 is dividing 8. So if x is dividing y, then I will write x dividing y. And if x is not dividing y, then I will write x not dividing y. Fine. So this symbol is clear, right? Now see the proof. To prove the first one, that is A plus C is congruent to B plus C modulo M, what we need to show that A plus C minus B plus C is divisible by M. This we need to show, right? Then our result will prove, right? Now see, we know that A is congruent to B modulo M, right? So this will imply M will divide A minus B. Got? So this will imply that M will divide A minus B plus C minus C also, right? We added a 0, so it will not change the divisibility condition. It means M will divide A plus C minus B plus C. So this is the proof, and this will imply that A plus C is congruent to B plus C modulo M. Got? Now for the second one, is AC congruent to BC modulo M? We know that M is dividing A minus B. This will imply A minus B is nothing but Km. Now if I multiply with C, then what will happen? This will come and then KCM will come. And this is nothing but AC minus BC. And that is equal to KC into M. So still this AC minus BC is nothing but a multiple of M. And multiple of M means what? This will imply M will divide AC minus BC, and this will imply that AC is congruent to BC modulo M. I hope you understand this proof, right? Now we move for the second property. Now question is what can you say about A minus C congruent to B minus C modulo M or not, right? This is true or not? So see, to prove this one, I need to show that B minus C. Now see, to prove this one, I need to show that A minus C minus of B minus C will be divisible by M, and this is nothing but A minus C minus B plus C, and this is nothing but A minus B. Now, because A is congruent to B modulo M, so M will divide A minus B, right? And this will imply M will divide A minus B is nothing but A minus C minus B minus C, and this will imply that A minus C is congruent to B minus C modulo M. So instead of writing just plus, I can write here plus minus, right? So now the next question. So this is true. Now the next question. A by C is congruent to B by C modulo M. Can we say like this? So let's take an example. 3 is congruent to 5 modulo 2. But 3 by 2 is not congruent to 5 by 2 modulo 2. Because this 3 by 2 does not belongs to integer. 5 by 2 does not belongs to integer. So we cannot talk about this congruence modulo here, right? So anything we cannot divide here, right? Anything we cannot divide. So which type of C is valid here? We will see later. So we will see later that for what kind of C is valid for this result. Got? Let's move for the next property, that is property number 2. So here we have one congruence modulo, and then we added one constant and multiplied and divided and subtracted. We talked about that. Now we have suppose two congruence modulo. Suppose if A is congruent to B modulo M and C is congruent to D modulo M. Got? Then what can you say about A plus C and B plus D? So the result says that this will also congruent to modulo M, and if you multiply these two congruent, that is AC and BD, then they will also congruent to modulo M. So to prove this one, now you take one particular example as we taken in the last cases, right? Here, that is 3 is congruent to 5 modulo 2. One more example you take and you verify that this result is holding. So let's, without doing those things, we go for the proof, right? Or better, let one take example. So 3 is congruent to 5 modulo 2, and now see here we are using, in both cases we are using M modulo M only, right? We cannot use two different modulo. And 4 is congruent to 6 modulo 2. So if we add, then 3 plus 4 and 5 plus 6 will come. So 7 and 11 will give you same remainder when divided by 2. So they are congruent. And 3 into 4 is 12 and 5 into 6 is 30, right? So they will also give you same remainder in modulo 2. So it's verified, right? Now see the proof. So we have A is congruent to B modulo M and C is congruent to D modulo M, right? So we can write as A minus B is divisible by m. That is m divide a minus b and m divide c minus d, right? That is nothing but a minus b is in the form of k1m and c minus d is in the form of k2m, where k1 and k2 belongs to natural number. Got this or not? Or we can say this is from integer. For into integer it is possible, right? Now see, what we need to prove? We need to prove that a minus c is congruent to b plus d. So for proving this, we need to show that a plus c minus b plus d is divisible by m or not. That we need to check. So this is nothing but a minus b plus c minus d, and that is nothing but k1m plus k2m, and that is nothing but k1 plus k2m. So it is multiple of m, so divisible by, it means what? M will divide a minus b plus c minus d, and that is nothing but a plus c minus b plus d, and this will imply that a plus c is congruent to b plus d modulo m, right? So this is the proof for the addition. Now let's move for the proof for product. So for proving product, that is AC is congruent to BD, I need to show AC minus BD is divisible by is divisible by M or not, right? Now this AC minus BD I can write as AC minus CB plus CB minus BD, and that is not but C into A minus B plus B into C minus D. Now see, A minus B is divisible by M, so it can be written as C K1M plus B K2M, and this is nothing but M common here, C K1 plus B K2. It means what? This is AC minus BD. It means what? AC minus BD is equal to M times some natural number or integer. So M will divide AC minus BD, and this will imply AC is congruent to BD modulo M. So these are the second properties. Now if I ask you this question, now again here the question is came that if I do A minus C, means I subtracted these two congruent modulo, right? Then they will be modulo M, congruent in modulo M. So you verify this is true, right? And if I ask you question that A by C is congruent to B by D in modulo M, then you verify that it is false, right? So these are two homework for you, right? So because in subtraction it is true, so I will generalize this result for minus also. This is true for minus also. Fine. Now we will move for the third property. So what this third property says, if A is congruent to B modulo M, then AC will be congruent to BC modulo MC. Fine. Here note that C has to be positive and C belongs to be natural number, right? Or we can rightly say C has to be natural number. Got or not? Got or not? So here we multiplied the C constant to A also, B also, and M also. So let's see the proof for this. So to prove this one, I need to show that MC divide AC minus BC, right? So for that, See, this AC minus BC is nothing but C into A minus B. Now because A is congruent to B modulo M, so I can write A minus B as K1M. K1 into M into C, that is K1 into MC, and this is nothing but AC minus BC. So this will imply that what? MC will divide AC minus BC, and this will imply that what? AC is congruent to BC modulo MC, right? So this is my third property. Now, now let's move for the fourth property. Fourth property is what? Suppose if we have A is congruent to B modulo M, then A to the power K is congruent to B to the power K modulo M, where K has to be positive, or we can say K has to be belongs to natural number. Then power K will also hold, right? So we have to take, for the proof is simple here, just take A congruent to B modulo M K times, right? And by the second property what is there? That is, if A is, by the second property what is there? A is congruent to B and C is congruent to D, then AC will be congruent to D. So if I multiply this K time, if I multiply this K time, then what will happen? A into A into A into A congruent to B into B into B up to K times, right? This will also K times, and this will be congruent to what? Modulo M. So this is nothing but A to the power K is congruent to B to the power K and modulo M. So hope this fourth property also clear to you. Now move for the fifth property. So we asked about the divisibility, right? That is, if A is congruent to B modulo M, right? Then A by C is congruent to B by C modulo M by C, where the C is factor of A also, B also, and M also. Like if we have a number A, B, and M, and if in all these three numbers C is a common factor, then if I divide also in all the three, then also they will maintain the congruence property, right? Suppose we take an example, 8 congruent to 12 modulo 4. Now here 4 is a common factor for each one, or we can say 2 is a common factor for each one. So if I divide all these numbers with 2, then it will come 4, this will come 6, and this will come 2. And 4 is congruent to 6 in modulo 2, right? So the fifth property says like this, means if C is a common factor in all these three, then you can do the thing, right? So this is the fifth property. Now let's move for the sixth property. So if A is congruent to B modulo M, right, and N is a factor of M, then A will be congruent to B modulo N also, right? So see the proof of this. You see here, N is a factor of M. It means M is equal to some K time N, where K belongs to natural number, right? Now we have to prove that A is congruent to B modulo M. So it is nothing but we have to show that A minus B is divisible by M. So This will imply a minus b is divisible by n also. Why? Because a minus b is nothing but k1 m type, km type, right? And m is nothing but k1 n type, so it is k into k1 n, right? So a minus b is a multiple of n, it means n will divide a minus b, and this will imply a is congruent to b modulo n also. So this is my sixth property, right? Now let's move for the seventh property. Property is generalized of the above property. So suppose if we have f of x, a polynomial with integer coefficient and a is congruent to b modulo m, then what will happen? F of a will be congruent to f of b modulo m. What or not? Means if you have a polynomial, then what will happen? And a is congruent to b modulo m, then what will happen? F of a will be congruent to f of b modulo m. Like example, 3 is congruent to 5 modulo 2, and we are taking f of x equal to x square plus 2, right? Then f of 3 will be how much? F of 3 will be 3 square plus 2, and f of 5 will be how much? F of 5 will be 5 square plus 2, right? Now see, 3 is congruent to 5 modulo 2, so this will imply 3 square will be congruent to 5 square modulo 2, right? And if I add 2 on both sides, then also they will be maintain the congruence modulo, right? And this will imply f of 3 is congruent to f of 5 in modulo 2, right? So like that this property is saying. So this is the meaning of this seventh property, right? You can go for the proof in the generalized form also, right? So if you want, then comment that I want the proof of this, right? Or if you want, you can try also. So the proof is very simple. You just take a generalized polynomial whose coefficients are integer, and then apply this above properties one by one, right? Then you will get the result. So I am skipping this proof, but if you want the proof, then you comment and ask. I will give that in a separate video, right? Now, so for today, this is enough, and we will see some problems after this, right? And after some problem, we will go for the next concept.